1 because we're saying a of I equals I, or do we not have to do that?
Your input is given from 1 to n, so you are going to be. Did my recording just stop?
It says it's still recording on this end.
Okay, I think we hit the 4-hour mark, so it's going to create a second recording. That's how long this has taken. So yeah, because your array is indexed from 1, you're not doing I plus 1 or x plus 1. You're looking for the exact index. So your index of 5 should match 5.
It says that there is an index I for I equals I because indexes are 0. If we're saying a of I, where I is a 0 x.
Sorry, can you type out your question? You keep breaking in and out, and I can't really hear you.
Yeah, I can type it.
Okay. Yeah, it's not starting from 0. You're very much given that it's starting from 1. It's defined right here. Okay. All right. So let's see. Next problem is 2.18. 2.18 is a thought experiment. Well, not a thought experiment. You're trying to explain why the fastest way to search a sorted array is in fact binary search. We cannot get a better solution than that. And the reason in the comparison search, anything that requires a comparison, okay? You can look this up. There's many ways to sort of explain this. This is the best I can do. This is fresh from me. No AI involved. I just kind of thought about it and wrote it, so it's not very like proofy. It's trying to be explain it through logic. Okay. So when you're doing a comparison search, right, the optimal solution would eliminate the most search space at a time. You're trying to get rid of as much search space at a time. And so your only decision really when you do a comparison search is everything less than equal to or everything greater than equal to. You can only really make a decision based on less than or greater than. That's how comparison searches work. Okay. Now, any solution that would say, oh, I can promise you I can get rid of 75% of the search space at a time, possibly, is only a best case. A best case would get rid of 75, let's just say that's what you find. The best case is going to get rid of 75% of the search space, which means on the other side of that, the worst case is that you can only get rid of 25% of your search space, right? Because you can only decide on one section or the other. And if I can get rid of 75% some of the time, that means I only get rid of 25% some of the other time. So at best, right, your best worst case is actually half. You get rid of half every single time. That's the only best case, the best worst case you can have. Otherwise, you could potentially have 25% each time all the way through, and you end up getting a worse runtime. So if half is the best worst case possible, in an optimal search, each decision must split the decision into 2 possibilities, and that results in a binary tree, which takes all of n to reach a leaf. So right, so like if I split my subproblems into a binary tree, at any given, my worst case is how long it takes to get to any leaf, and that is O log n to get to a leaf. Hopefully that makes sense. For anything that you could try to get better than 50-50, it's going to be 75-25. It's going to be 70-30. It's going to be 80-20, right? And your worst case is going to be even worse than 50-50. So you can't do better than it. Okay. Any questions about this particular logic? It's not really a proof. It's just sort of, talking your way through it. All right, cool. 2.19. 2.19 is about understanding the merging of merge sort and why it's actually, it makes the sort optimal. By the way, there is a second section, a different section in the book. I forget where it is. I think you can look for it. That actually also says that the best worst case for a comparison sort is O of n log n. It's very similar to the explanation I gave for log n to be optimal search. O of n log n is actually optimal for worst case sorting. The reason why we have so many different sorting algorithms isn't because we think the worst case can be better than O of n log n. That's been proven. We know that the worst case is O of n log n. What you can do, though, is you can get better search algorithms for the most realistic case or for most cases. And that has gone through evolutions over the years. I think there was merge sort is what I want to say Python used for a long time, and then some guy named Tim created this thing called Tim sort. And so the Tim sort was based around the idea that even though worst case is open login, most real life data has runs in it. And so if you can predict and search for those runs, you can do a better sort by not having to just go through the entire worst case. And then there's a new update recently to Python. It was, I forgot what the name is. Power sort? I think it's called power sort. I want to say it's power sort. Yeah, power sort. 2025. Is that really when it was? Okay. So the worst case scenario for power sort is also O of n log n. But it's actually generally almost linear time. Just because of the way it's super complicated, way too smart for me to explain. But again, it uses the idea that you can predict where the runs are so that you don't have to do a full sort every time. So fascinating topic, still being discovered and still being researched on how to do a faster real life sort versus what a worst case is. But nobody's ever trying to beat O of n log n worst case sort. So super cool. All right. Sorry, I got off topic. It's just really, really cool topic for me. A k-way merge operation. Suppose you have k sorted arrays, each with n elements, and you want to combine them into a single sorted array of k n elements. You have two strategies. One strategy is to use the merge procedure from 2.1, 2.3. I don't have reference to it, but you merge the first two arrays, then merge in the third, then merge in the fourth, and so on. What is the time complexity of this algorithm in terms of k-n? So this would be like, if you were doing merge sort and you just merge all your subarrays together as opposed to merging them two at a time. And then B is give a more efficient algorithm to the problem using divide and conquer. And so the first one is so merge sort takes n merges at each occurrence and does log n merges, so it's all n log n. So similarly, there are nk merges at each occurrence. You're possibly merging, it gets bigger and then you keep merging in one array at a time. But you do this k times because you have k arrays. So you end up with O of nk times O of k, which gives you O of nk squared. Okay, so that's how many merges you have squared times the number of elements you have. But if we do what merge sort does, which is we divide the k arrays into k over two pairs and merge them similar to how we do with merge sort, then since they are sorted, the merging behaves in the same way. We continue merging the combined arrays in pairs until we have one single sorted array. So there are nk merges, but you only do it k times. So it's the same number, number of merges at each recurrence, but rather than do it k times, you do it log k times. So you end up with a runtime of nk log k. Any questions about this particular problem? Jafar?
Yep. So sorry, but I did not understand a lot. But first of all, I want to ask, what does they mean by merging the first two arrays? So merging the first two array, if we have n and n, so this is 2n, and then sorting this array, it will be 2n log of 2n, which is n log n. Then we multiply that by k, because we have k times to redo the same, it will be nk log n.
The very first one?
Yeah.
Okay, so what it's asking you is where's my so your arrays are already sorted, which means that if I was to take these arrays, okay, and if I was to combine these two arrays, I will have done some kind of comparison, like so, right? Like how whatever your merge technique is, your merge technique, you do that, right? And then if I was to merge this array in again, I would do the exact same thing with this bigger array, with this array. And then I would take an even bigger array and I do it with this array. And every time you do that, you end up doing a k-in merge k times, right? As your array gets big, it just continuously gets
Okay, so the size of the array
merges.
is not n, it's kn, because you are adding
the
k.
size
The
of
worst case, the worst case is kn. So this is why we have kn times log of kn, and then you multiply by k. Okay, now I understand.
Okay, great.
Okay, great. And for the second one, for the second part, I was of the idea. Okay, I think this is not divide and conquer, but to put a pointer for each of them, each of the n, and going together. So based on this pointer, you put the minimum first, then the minimum after it, then the minimum after it, then the minimum after it, till you finish the first set of things.
Yeah, I mean that's just merging. That's just you take your merges and you just bring the smaller of the two arrays, and that's exactly what merge does in merge sort.
Okay, thank you.
All right, Manjanatha.
Joes, for the second one, I tried to apply the Master's theorem, and then I think I got a different answer because I was looking at how do you divide the big array, right? It's nk over 2, right? That is what your total array size is nk, and then you divide it into nk over 2, and then you keep on recurring.
Why do you do nk over 2?
Because your overall, there are k arrays with n elements in it. So that will be n multiplied by the k. That is your full size of the input, right?
Right.
So, and then when you divide it into two pieces, that's nk over 2 subarrays.
Well, you don't do that because you started off with k sorted arrays. You're not dividing them anymore. You're only considering the merge step down. So you're not considering the division of it. You wouldn't divide it any more than it already is because it's already sorted, right? So you're in the middle of merging them. So
right,
but you don't do it over 2.
Your whole size is nk, right? And then when you take two halves to feed it to an algorithm, then it's actually nk over 2, right? That is your left size, and nk over 2 is another right size, right side, isn't it?
Yeah, yeah, but like nk over 2, the runtime of that merge is still nk. Like nk over 2 is the 1 over 2 is a constant, so you don't really, it's still nk for the merge.
The merge is like, actually I put it into like like, T of n is equal to 2t nk over 2 plus big O of nk. That's what I got. Maybe right side was problematic for me. If I put it into this form, it was coming to nk log nk. So is it possible to put it into that Tn is equal to 2t nk over 2 form and then see how it works out?
I don't think so, because you have 2 terms.
Yeah.
Yeah. So you just have to kind of reason it out, or I think you can also use substitution. But like, I know that each merge is nk, because no matter what sub size of that, right? Like if I divided by 2, divided by 4, like it's just ends up being a constant multiplier. So it's still nk in terms of merging. And then I know I have log k because I am doing pairs 2 at a time. So that's how many merges I end up having to do. So log k merges times the amount of work it does to merge is nk log k.
I see. Okay, thanks.
Yeah. So your merge time is the same in both cases. It's just how many merges. Are you doing k merges because you're doing 1 at a time versus log k merges because you're doing 2 at a time.
Yeah. Yeah. Thanks.
Yep. Winston, and then we're gonna move on.
I just had a question about the mechanism of how we would merge, because in merge sort, we get down to one item in our recursive call, and it's by definition sorted, and then we merge it with another item, and we kind of linearly combine them. So if we were doing, yeah.
So imagine you've gone down to your single subproblem on merge sort, and you're bubbling your way up, and then at a certain point, I say, okay, now that you have k subproblems, each of the same size, keep merging them. And that's basically what this problem is saying. You have k sorted arrays and you're merging them. So it's just like somewhere in the middle of your algorithm on the way up.
Gotcha. But it's
and
like
it would just be merged in the exact same way. You just compare one element from both subarrays, and then you say which one is smaller, take that one, and then you take the next item from that subarray, which one's smaller, and you take that one, and you just keep going down both arrays, and then you merge them. So it's like the exact same merge step.
Okay.
Yeah.
Okay, gotcha.
You just don't break them down because you're already on the recursive path back up.
Gotcha. Makes sense.
Yeah. Okay. Any questions? Any more questions? Okay. So now we have 2.22. .22 is a serious problem. You're given 2 sorted lists of size m and n. Give an O log m plus log n time algorithm for computing the kth smallest element in the union of the 2 lists. So first, you're not always given the runtime, so be careful of that. And so we have 2 sorted lists, which means we kind of want to consider some sort of binary search. We're also looking at the kth smallest, so we might be considering some sort of selection algorithm. But we want a solution that's O of m log m plus log n, which means that a selection fast select approach would be too slow. That would be O of m plus n. We also definitely don't want to try sorting anything or resorting anything, because that's just going to be slow, right? That's just not a good idea. So what you end up wanting to do, it turns out, is that you want to take your first array and you want to take your second array And you kind of want to stack them like this visually. Think about this. You want to stack them like this, where the this smallest number is less than this number, and this large number is less than this number. Now we can potentially, you know, because we don't know anything about the arrays, it could also potentially look something like this. Right? So we stack them like this, or we can potentially do something like this, or you know, one of these combinations, right? Either all the green is overlapping to the left of blue, or blue is to the left and overlapping with green, or all of green is held within the bounds of blue, or all the blue is held within bounds of green, right? Now, once we have that, and we're trying to find the kth smallest element, what we're really saying is that if I cut off here, okay, this number, let's call it in prime. These two numbers add up to k. If these two numbers add up to k, then my kth element is somewhere along this line. Okay. Similarly, we can do the same thing here, where you know if these two, the amount of elements here and the amount of elements here add up to k, then my my kth element is somewhere here. For this, you know, same thing, right? Like if these two add up to the number of elements here, k, and so that's where what you're doing. You're trying to draw a line through where the two arrays kind of line up visually, and say everything to the left of this added together, however many elements those are, adds up to k, and therefore one element in either the green or the blue right there is my kth element. Okay. And what you can do in order to find that is you can eliminate based on a process of saying, okay, well, if I compare the midpoint of these two things, I know everything on the left of one midpoint on the green side is less. Everything on the right side of that midpoint is more. And since I'm looking for a k somewhere in between here, I can eliminate all of that. So you're doing a binary search across two arrays, and it's tricky to set up, but I will post a solution and we can hopefully talk about it. Okay, so I'm gonna make it a little bit easier to explain by saying that CK is the current K we're looking for, because whenever we adjust anything, if we eliminate things that's above K, it doesn't matter. Our K is still the same within our search space. But if I eliminate anything to the left of K, my K is no longer the K, the same K for the limited search space, right? So like if I'm looking for the 100th smallest value, if I eliminate the largest values from 150 on, whatever I'm left, I'm still looking for the 100th smallest value. But if I'm looking for the 100th smallest value and I get rid of the 25 smallest values, I'm no longer looking for the 100th smallest value. I'm now looking for the 75th smallest value with whatever is remaining, right? So you have a current K you need to get track of, okay? So again, the middle index of M, which is one array, and N, which is as my mids for those two, right? And we're going to set our current K to the K we're looking for. If the two bits added together, okay, so our the middle index of the two together is greater than or equal to our current K, we want to discard the right half of the array with the larger mid element. If they're equal, just pick a right half to discard. It doesn't matter. Now we set the current K to itself. If the two midpoints added together is less than or equal to our current K, we want to discard the left half of the array with a smaller mid element. If they are equal, just pick a left half to discard, whatever. And now we have to update our current K to be the smaller of the mid index because we have removed that many elements. Okay. Note that both of these can happen at the same time. if n mid plus n mid equals ck. Now, if they happen to both times, you can eliminate both sides if you needed to. Okay. We continue until the following base case. Once we have discarded all of one array, so if everything in one array has been discarded, then we return the ck element in the remaining array. Because we have eliminated an entire array, so imagine a situation where these two arrays are like this, and my kth element is actually somewhere here. So if that's the case, there is a potential where I get rid of everything that's in the green array plus some in the blue array, and my my ck element has to be in the blue array somewhere. Okay. The other way can happen too. If we say that we are actually looking for something, say right here, we could potentially eliminate everything that's in the blue array, some of the green array, and my ck element has to be somewhere in the green array. Okay. So that's what that base case is saying. If you eliminate all of one array, then return the ck element. And in fact, that's actually what we're looking for, because even if our ck element is right through here, right? I'm eliminating half of my one array or the other at a time. So if I start off with my algorithm and I eliminate this half, and I continue and I eliminate this half, right? And then I continue more and I go, okay, well, this half I want to eliminate this, and then my green half I want to eliminate this, right? At some point, I'm going to get less and less and less and less. And I'm going to start eliminating the other half. I'm going to switch sides and say, okay, well, now my midpoint of whatever's remaining in green might be greater than whatever's remaining in blue. And so eventually, I'm going to keep eliminating from both sides. And eventually, one of these arrays is going to get eliminated entirely. And once that array is eliminated entirely, I can make a decision on where my ck element is on just the remaining array. Okay? All right. So let's explain the correctness, and hopefully this makes more sense. Suppose that n mid and n mid is greater than my current checkpoint. So that means that this midpoint plus this midpoint is to the right of my the ck I'm looking for. Okay. Then we know that the larger half, right, based on the two mids, can be discarded, right? So like if these two mids, right, end up greater than this, I immediately know that this entire half is not needed, right? Because everything here is too big, right? My ck element is somewhere it's somewhere to the right, and so everything beyond this part right here can be immediately eliminated, right? That's because everything greater than the larger mid of the element has to be greater than the ck element, because the elements are greater than my my ck, and therefore I can eliminate the bigger half immediately. And the similar situation on the other side, if my n mid and n mid is less than ck, that we know that I'm too far to the left, and therefore I can eliminate a smaller half of the left of the smaller halves, because that is all going to be less than my ck, right? And because of that, we have to recalculate our ck, because if we remove 50, we're not looking for the same k anymore. We're looking for a adjusted current k value. Okay. So we move from that k value how much of the chunk that we've just removed. Okay. Once all the elements of one array is discarded, because we've eliminated whatever's right, because they are either too big for ck or smaller than ck and accounted for because we adjusted it, then whatever is left in the remaining array can be used to find the updated ck element. This element is the original kth element. Okay. The runtime here is we are performing a unified binary search across M and N, right? We are eliminating half of each, at least half of one array at a time. Each time we perform our check, we discard half of one of the arrays. We can do both. It's a possibility, like I said, if the mids are equal. But worst case, we are only eliminating half of one array at a time, and this results in the combined runtime of log m and log n, and that's your final runtime. Okay. All right. Questions about this problem, particularly if you are going to do the programming problem, it is a slight variation of this problem, and so if you want some hands-on experience on trying that, I suggest doing the programming problem. All right, Jafar?
Yep. So I want to ask here about the base case. So whenever you are eliminating everything till the end, so we'll still have all eliminating left or right. Yes. So if we take that right now k is equal to 2, and you have only one element in the first one and the second element in the second one. So this is the base case, and then we return the 2, so it's the bigger one. And if it is 1, we return the smallest one. We need to write this or no? Or
sorry, if you have one in the left, one in one array and 2 in the other array?
No, I'm saying, okay, if we continue this algorithm till the base case, we will have only one element in the first array and one element in the second array. Is that true?
Okay.
And k equal to 2, 2 or 1. One of the so either k will be equal to 2 or k will be equal to 1 at this time. Because you are eliminating everything, you are lowering k. At the end, you will have either k equal to 2 or k equal to 1. So 1, we will return the smallest one, 2, we will return the bigger one. Or the base case is different from what I'm thinking. Can you take an example and continue to the end? So let's take, for example, 3 items and 3 items and try to do the base case.
So what is your 3 items?
1, 2, 3, 4, 5, 6, something like that, or
And we are looking for, let's say,
fourth element, for example.
Fourth element. So we are looking for this one, right? Okay.
Yes, this one. Yes.
So we take the midpoint of 2 and the midpoint of this, so that's 7. And since that's greater than our numbers, right? We
eliminate 6.
Huh? We eliminate 6. Okay.
Yes. And k was still 4. Yes.
K is still 4. Okay. So now we take the midpoint and let's say we just pick one. It doesn't matter like how we do. Let's say let's go with the lower one. So we have 4 and 2. So that's 6. And that is greater than our CK. So we remove this value, right?
No, 4 and 2, that's
6.
6, okay.
Which is greater than 4 or greater than the k equals 4.
Okay.
That we're looking for. Okay. So we limit that. Now, so the midpoint, let's say, is 4. 4. Yeah, so I think the basis might be if I'm left with one value on one of the arrays, I should be able to calculate the. Oh, what I? So it's 2, 6.
No, it's not 6. This is what I think. It's still 3 in this case because we are counting. The k is the counting number. The kth element, so it's not the sum of the elements. It's the kth element.
Oh,
so the index k is 3. And therefore we are eliminating, it's less than 4, so we are eliminating the smaller one, which is 1 in this case. So first we eliminate 6, then we eliminate 1. Not 5.
Correct.
Okay, it's fine. And then at this point of time, wonderful.
Okay.
Now we have 2 and 4, and k is 3 because we decrease it with 1.
Right.
And because 2 and 4, it's 2, which is less than k, so we are eliminating 5 at this time.
Okay.
And k will still be 3, and then at this point of time 2 and 4, and k here is 2, which is less than 3, so eliminate 3. And finally we have only 2 and 4, and k is 2. At this point of time, this is the base case.
Yep.
Whenever we have only 2 elements, I think I'm saying this because in my opinion I need to write this in words. So whenever we have the base case, which is 2 elements left, if we have k equal to 1, we return the minimum. If the k equal to 2, we return the maximum. Or we don't need to go that deep in the description.
So my CK right now is
2.
2.
Yes.
Okay. And so middle index here is 2. Middle index here is 1. So my is 3. And we decide that if 3.
No. Mid of index, the first one is 1, still 1, because it's relative, as you said, it's relative to the array. Yeah.
So it's 1, so that's 2.
Yeah, which is equal to CK.
Which is equal to CK, which, okay.
At this point, we need the base case. We need to write a base case here.
Yeah,
okay.
That's right.
Okay, thank you.
Everybody gets to learn today, including myself. Like that. Okay, how's this sound to you? Once we have discarded all of the array, or there are 2 elements left total, we return the CKth element of the remaining elements. Because you have 2, then it's easier to do. Okay.
Yeah.
Cool.
Thank you very much. Thank you very much.
Thank you. All right. Vikash?
Yeah, so on similar note, when we say once we have discarded all of one array, but would we ever reach that base case? Because I'm not saying, if I understand correctly, we are not discarding the mid number. We are discarding either the left or right of the mid number. That basically means when we have one element left in the end, we're never gonna discard it. So would we ever reach a base case where we have discarded all the numbers from one of the arrays?
Yeah, this is what we just talked about, I think.
Right. Similar note, right? Yeah. And
yeah.
I almost reached the same solution, and my base case was basically whenever there's one element left, just check if it is greater than all the elements, or the biggest element in the other array, or smallest than the smallest element in the other array. But I don't know if that would work.
Okay. Trying to think. Yeah, because the mid element doesn't ever get discarded.
Yeah, I'm sorry. Let me reword my base case. So basically, what I was checking was if the first element of one array is bigger than the kth element of the other array, then just pick the kth element of the other array. That's the base case.
Okay. Yeah. I'm gonna go back and let me put a question mark here too. And reformulate this, and then I'll post it back on the thread. Hopefully, it'll be correct. Okay. Karishma?
Hi, can you hear me?
Yes.
Okay, so my question was, when I finished this problem, I first did one where it was merging up to k elements, would be at most O of k. The second approach to it was doing the fast select on a virtually defined array of the two, so it would be O of plus n. I know those are not obviously the optimal solutions, but I was just wondering what you think are the deduction for having those two approaches.
Oh, I can't do that. I would not be able to properly give you a what that deduction was. So it would depend on the head graders and how they decide to calibrate that.
Okay.
I wouldn't know. Yeah.
On a discussion they did when they posted this problem, they had put to like a suggestion about you should go about using a merging approach and then a median of medians, and that's why I did those two ways. And I didn't think of the other way. So that's why I was just curious to how far off I was.
Yeah, I don't want to try to grade that without like actually having this as a proper homework problem.
Okay, no worries.
Yep. Lanfen?
I wonder if you compare, I'm not sure if I read the question clearly or not. My understanding is for this two array, do you want to compare one array's lower bound and another array's upper bound to see they happen not to be overlapped? So this will be very kind of simplified version, right? So you just look for the k in one of the array at all at the end. Does the question mention that they should be overlapped?
You can potentially change the base case to something like, if one array, the minimum of one array is clearly bigger than your k, then you can immediately be able to return your solution. And I think that's actually going to be the base case I want to try to work out. I think that actually works better.
Okay, thank you.
Yeah, because eventually you're going to eliminate all. You're going to keep eliminating until one of your arrays are going to be above your check.
Another thought is why not to merge these two together? Then you take about m plus n steps, and then you just work on the union, the updated union, list to find the case out.
Because if you merge, because if you merge them, then you're either going to be O of.
Oh, I see. It's kind of you're taking another merging the sort.
Yeah, you're doing the fast select. Yeah.
Okay,
you're gonna
okay,
get a worse runtime than that. Yeah.
Got
Yeah,
it.
you
Thank
don't
you.
want to do that. Yep. Shanek?
Yeah. Hi, am I audible?
Yep.
I have two questions. So I guess it's getting late, so I don't know if you will be able to answer now or I should post it in the thread. I was wondering like if there is a different way to do this where we look at the k by tooth smallest or k by like half of k smallest element in both the lists. And then based on that, proceed to eliminate pieces of the list that are, outside that bound. Has that also been done?
I would suggest any solutions that you think is a good approach. You post it in the practice threads and have others doing like there's going to be like 100 of these, and I won't be able to like
I see. Okay.
Yeah.
I guess the second question is like, how do you come up with an answer like this on the fly on the exam? It seems pretty difficult. I guess how would you suggest thinking for problems like these? Because it seems like for DNP or dynamic programming problems, I guess there are more examples of things to look at. And they do have a certain pattern to them. But for divide and conquer, it seems like there are a lot of things you have to do sometimes to get it to a stage whether it resembles like a binary search or a merge sort, or you have to change things in ways that are not always intuitive.
So I've covered this in previous office hours, and I'm gonna restate it. It would be unfair for you to see a problem like this for the first time on an exam. And I think that's like, what we're trying to do is that you are not going to see a problem where you have never seen a similar problem to it before, or you are going to have to come up with a really, really like imaginative or new way of solving the problem. Any problem that you get will be similar enough to a problem you've already seen that we feel it's fair for you to see the problem. If I was to give you this problem on the exam for the first time and you've never seen a problem like this, I would expect you to do poorly on the exam, and that is not something we are trying to do to the students.
Understood. Okay.
Yeah.
Thank you.
But having seen this problem, having seen an approach to it, if you saw a problem similar to it with a few adjustments, a few tweaks here and there, we would expect you to be able to answer it. Not that you've seen an approach to it.
Okay. Yep. Understood. And I guess continuing on, so there are some problems in the suggested problem list that deal with matrix multiplications, which wasn't covered very extensively. Like, like the problem number 27, I think, or 26. I forget the exact number, but it's on the thread for suggested DNC problems. Do you think like you would have a follow-up hour for those, or because even the lectures didn't touch too much on DNC problems applied in
I think the problems that are said, hey, these are kind of stretch goals or these are complicated problems for you to kind of work out are really just like extra problems that you can do. But I wouldn't say that that's something that you need to be able to figure out to be successful on the exam.
I see.
So the reason
Okay.
I don't cover them is that they're particularly hard, and I think it's, for the particularly hard problems, if you are at the level where you want to be able to solve those, then you should be working on those and working with other students to get a solution. Hearing me give you a really complicated solution to a very complicated problem, I don't think benefits you for the exam.
Yep. Okay. Thank you so much. That's all from me.
Yep. Okay. So that is the end of our office hours. I will not be having a follow-up session, but if you ask questions in the office hour thread or the practice question thread, then hopefully other students or other TAs will be able to answer you, including myself. So that's it. I have a couple of hands up. I will answer these and allow people to go to dinner. Winston?
Yeah, just quickly. So if I got it correctly, the other suggested problems for dynamic programming are ones that like 220, 227, 228, 232 may not be the best area to focus our attention on for the exam. If we'd like to, we can explore those later, but not something we'd be expected to be able to solve on the exam. Is that correct?
Which of the problems? Sorry.
220, 227, 228, and 232 were the other problems that were provided on the dynamic programming.
Do you mean DNC? Because those are DNC.
Sorry. Yes, you're right, DNC.
I would say go over 220. 220 is a good exercise to understand why comparison sorts, comparison sorts are the way they are versus a linear time sort, which can exist in very specific situations. I would post that and talk to other students about it.
Okay, thank you.
I think 220 is an interesting one. The other ones are probably too advanced for the exam.
Okay, thank you so much.
Yep, no problem.
Yep, I want to thank you very much. Yes, I want to thank you very much for the session. That's it. I don't have a lot of other questions. I hope we do good on the exam also. So
yeah, I
see
am
you soon.
hoping all of you wreck the exam and you don't have to see me in future semesters. I hope everybody does really well. Yeah, so a few parting words. Like I said, go into the exam, be confident. Just like an interview, your attitude is going to influence how well or poorly you do on the exam. So if you go into the exam thinking, I'm going to enjoy this, I am going to get an A on this exam, and I am never going to have to think about dynamic programming again, that is going to be hugely helpful. Talk to other students, talk to your TAs throughout the week. I think we don't actually have that much conversation going on in this class, which is unfortunate. Be lively, be able to ask questions about anything that you need help on. TAs will be available. We want you to do well on the exam. We really do. And finally, every class needs like I say this, you need a hype person. You need a person in your cohort to basically lift up everybody's spirits and get everybody motivated and get everybody excited about taking the exam and doing this class. So if you want to be that hype person, feel free to go and chat people up in chat. During my semester, everybody remember. I remind them that I was the hype person for my semester. I told everybody we were going to pass the class. I told everybody we were going to get an A in the class, and we end up doing my cohort did extremely well in the class, and I think it's because I basically lifted everybody's spirits. So having a positive attitude goes a long way. So good luck to all of you, and I hope you enjoy the exam. Lampan, final question?
Sorry, I have the last question. Just maybe it's helpful to everyone. Given those like the materials we've been working on, such as the quiz, we have like 3 quiz and 4 homeworks, I think, and plus like two like practice questions, right? Homework practice question 1 and 2. If we only focus on those things, review them, do you think it will be helpful? That's my plan because I don't think I have time to work on any extra work. And besides, I didn't have chance to work on the practitioner exams questions at all by myself. So I would just purely maybe revisit your video and then go back to understand the question, the solution pattern. That's my plan. So other than that, what do you recommend? If this sounds like a reasonable study plan for this exam?
Every student's a little bit different. There's some general guidelines. Like I said, I would definitely make sure that you understand the core of the lectures. The lectures are super important to understand. From there, I think the assigned homework problems are really important to fully understand. Like you should be able to solve that problem, within 25, 30 minutes if you see it all over again. So I think the homework problems are super important. The practice problems that we give model solutions to are the next priority. Those are the questions that we think you should, if you want to go, you should focus on beyond just assigned homework problems. The practice problems that I went through today are sort of like, the final, to us, like the final material that, should set you up for success. Like you shouldn't need to go beyond that. You shouldn't need to go online and look for additional problems. This set of practice problems is really like the absolute like max that we would expect from our students. And if you end up thinking, oh, I need to budget my time based on how much time you have, like I said, start with the assigned homework, go with the model solution homeworks, and then go with the practice problems as much as you can. Okay.
What is a model solution homework? I just don't know what that is. A quiz?
So yeah, so on homework 1 and homework 2, there was a set of practice problems, and those practice problems, if you go into your files in Canvas under homework 1 and homework 2, have model solutions. They're solutions that the TAs have released to you as this is what those solutions are and how you should write them. And those are important for you to understand what the solution we're looking for is. I also go over them in the previous 2 office hours, but those are the model solution practice problems is how we set it up.
Oh, okay. So because in your session, you always give us extra. Okay, got it. Thank you so much.
Yeah.
Okay.
Yep. All right. And I think that is it. I am going to stop the recording and call it a night. There won't be office hours next week because it's the middle of the exam window. But when I see you guys next time, we'll be going on to graphs, and graphs is fun. So I'll see you then.
Thank you. Bye.
Thank you, Joves.
Thank you.